The topic of this lesson are things that I'm going to call parallel plates, but depending on your background, you may have heard of these things, maybe in Mr. Webb's class, technology class, you may have heard of these things called capacitors. They're synonyms, they're the same thing, just sort of the physicsy name for them is parallel plates. When we start using them in circuits, they call them capacitors. What these things look like is literally two pieces of metal, two conductive materials, parallel to each other, separated by a bit of an air gap, so they're not actually touching each other, and connected to a battery. We're going to say that the battery has a voltage of V and the distance between the two plates is D for distance. When we first connect the battery to this, or maybe if there was a switch and the switch was open so current couldn't flow, and then we close it so current can flow, but when it's first set up, so think way back to grade 9, the little terminal of the battery is the negative side, the bigger terminal is the positive side. Electrons get pushed and pulled through those wires. Electrons would repel out of the negative terminal and go this way, the way this one's drawn. Electrons would collect in this top plate, and electrons would then, the electrons in the bottom plate don't like being close to the electrons in the top plate, so they would be repelled away from those negatives, pulled towards the positive terminal, making the bottom plate a positive plate. So if we set up a parallel plate or a capacitor, as soon as we connect the battery, it's going to push some electrons around. The way this one's wired, the plate that's connected to the negative terminal, in this case the top one, it would become negative. The plate that's connected to the positive terminal, it would become positive. That's what happens when you first connect it, but over a bit of time, the current stops flowing. The voltage of the battery can only push these electrons so hard. So at some point, the top plate, well in this case the top plate, the negative plate is going to become so negative the battery can't push any more electrons in there. The bottom plate, or the other plate, is going to become so positive no more electrons are drawn out of it. So after a bit of time, the current actually stops, and when we get to this point, we could say that the voltage across the plates is the same as the voltage of the battery. If we had a voltmeter and connected it to the one plate and to the other plate, it would read whatever voltage the battery had. How long that takes and how much charge that ends up on those plates, that depends on the voltage of the battery and literally the size of the plates. If those plates are really big, literally more physical space, then more electrons would pile onto the negative plate and more electrons would get pushed out of the negative plate. That's a parallel plate capacitor. What's kind of neat about it, we're not going to do much with this part of it because it takes some calculus, but the current changes over time. If you have a capacitor or a parallel plate in a circuit, so sort of grade 9 circuits from grade 9 science, if I gave you a circuit with a parallel plate in it, at first the current would be rather large and then would over time gradually slow to no current. Doing like voltages and currents and things like you did in grade 9 on circuits would be a little bit tricky if there is a parallel plate in your circuit because of that change over time thing. So usually, depending where you get to in university, maybe you'll circle back to these when you have a bit better calculus. Once you've got a parallel plate charged up, then it's literally like its own little battery. It's got a voltage across one plate compared to the other, so there'd be like a voltage drop from here to there. So it literally behaves like a little battery. I'm so old I still remember clock radios. So on bedside tables, people would have a clock radio so they could see what time it is if they woke in the nighttime. They used to literally have a battery in them so that if the power went off, your clock radio would still keep track of the time. In newer ones, they've put a parallel plate into those sort of clocks, and when the clock is plugged into the wall, one of the things the electricity from the walls does is charges up this parallel plate. Then if the power goes out, there's logic built into this clock so that it knows no power coming from the wall, take power from the parallel plate and use that power to run the circuit that keeps track of the time. So that when the power does come back on, the circuit's been sort of ticking away doing its thing and your clock still shows the correct time. So instead of a battery backup, it's a parallel plate backup. I'm so old, I remember when we used cameras instead of phones to take pictures, and in some cameras there would be batteries in the camera to power the flash, but the flash took more electrical burst of energy than the batteries could provide. So the batteries would charge a parallel plate and when you took a picture, the parallel plate basically short-circuited itself to provide a really intense short burst of energy to power the flash of the camera. So take a picture, flash will go off, but then with parallel plates there's this time thing, so it would take a few moments for the parallel plate to recharge off the battery so the flash would work a second time. So you couldn't take two pictures one after another really quick. Well, two pictures with a flash. Once the flash went off, there'd be a little bit of a delay while the battery recharged the parallel plate so the parallel plate could power the flash. So if you've ever seen one of these old cameras, or maybe in a TV show or in a movie, if a character says, oh, we've got to wait for the flash, that's what they're doing. They're waiting for the parallel plate to recharge. I didn't type it on here, but parallel plates, when they're used as capacitors, they also have the property of smoothing out any surges in electricity. So sometimes they're used in circuits to protect sensitive equipment. So adding a parallel plate or a capacitor sort of smooths things out so a surge wouldn't damage anything sensitive. If you do take an electronics course and start seeing capacitors, they don't look like how I drew them above. They're going to look like a little cylinder. And to save space, they take the plates, they have to put a material in between them so that the plates stay separate from each other. So they put an insulating material. The insulating material is often called a dielectric, so you may hear of dielectrics or dielectric constants. So they wrap a piece of metal, put a dielectric, it literally could be like paper, then another piece of metal to act as the other plate. To make it small, they wrap it up into a cylinder, have a terminal for the negative to connect, a terminal for the positive to connect, and there's your capacitor. The units for capacitance, if you ever take apart some electronics, if you see a little cylinder and it's got something like something labeled on it like microfarads, sorry, pen is struggling today. The unit for capacitance is capital F, farad, after Michael Faraday. So if you see something in a circuit labeled microfarad, usually micro, maybe sometimes milli, but with a capital F, that thing you're looking at is a capacitor. Out of all the cool things that capacitors and parallel plates do, the focus of this course is we're going to bring it back to their electric fields. When we connect a battery to a parallel plate, the one plate becomes negative, the other plate becomes positive. Electric field, by definition, is always the direction a little positive will get pushed or pulled if it were existing near those charges. What's cool about a parallel plate is in between them, if we put a little positive somewhere, it's always going to get attracted up to, well, in this case up, it's always going to get attracted to the negative plate. We could put it up here near the negative, it still gets pulled upward. We could put it down here near the positive, still gets pulled upward. Doesn't matter where we put a charge in between these two parallel plates. If it's a small positive charge, it's going to be pushed away from the positive plate, pulled toward the negative plate. What we get inside a parallel plate apparatus is a nice uniform electric field. It's the same value, the arrows are all the same length, the arrows are all the same direction, they're equally spaced, so we get a uniform electric field in between parallel plates. That's different than we saw with little bubbles of charge. Like if you had a little circle charge, the electric field points in all different directions. Let's say you had a little positive circle of charge, the electric field points away from that, so maybe up when you're above, down when you're below. The spacing between the arrows gets less as you're farther away from a bubble of charge, meaning that the electric field gets weaker when you're farther away from it. That's not the case with a parallel plate. No matter where you are between the two plates, the electric field is constant or uniform. Alright, we need to do a little bit of math. I didn't create a separate video for this, but the math isn't too bad. There's something called the parallel plate equation, and jumping ahead, the parallel plate equation connects the concept of energy to the concept of force. To get to our equation, we're going to imagine we've got a parallel plate, and we're going to take a little charge of Q, and we're going to push it from the negative plate all the way across to the positive plate. Because the electric field is uniform, is constant, we can use the simple version of work equals FD. Earlier in grade 12, we had to use some crazy calculus and area under curves to find energy or work. In this case, we don't have to. We can go back to that simple grade 11 version of work because the force is constant. So we know that work equals FD. And again, a grade 11 thing, if you do work on an object, the object gains energy. In this case, we can call the energy EE for electric energy, not a vector. So capital E for energy, the subscript E for electric energy. The work done is equal to the energy gained, so we can actually say electric energy is equal to F times D. Now, the things we talked about when we learned about electric field is electric energy is related to voltage. I'll doodle it off to the side. Voltage, by definition, is electric energy per charge. So if we flip the Q to the other side, we can say that electric energy is Q times volts. So on the left, we had electric energy equals FD, so we're going to place the electric energy with QV. So QV equals F times D. Similarly, when we learned about fields, the definition of an electric field, so this one is the vector, E with the vector hat, is the amount of force per charge. If I flip the Q to the other side, I can say that force is equal to electric field multiplied by Q. So wherever I see F, I can substitute in Q times E. This E, the bolded one, when I type it, I'm not very good at putting a vector hat, so the bolded E is electric field. So on the left we had QV, now on the right we have QE times D. The Q's cancel, so it doesn't really matter what charge we're pushing around in there. We get this new equation, voltage equals electric field times the distance between the plates. V equals ED. That's our parallel plate equation. We're going to use that for the applications we're doing in this course. It's kind of cool because it takes this energy quantity and relates it to a force quantity. Alright, out of all the cool things that parallel plates are used for in grade 12 physics, we're going to focus on two of them. There's little videos here talking through how to do it, so I'm just going to give an overview. The one thing we're going to talk about is if we took parallel plates and orientated them, I don't know if that's a word, positioned them so the plates are horizontal, then we could stick a charged object in between there and make the charged object float. The way that this one is drawn, it's the same as the other one. The bottom plate would become negative, the top plate would become, bottom plate would become positive, top plate would become negative. That means that a little charge in between there, if it was positive, it would repel from the bottom plate and it would float. I've asked a couple questions, the one check-in. Whenever things are floating, the key thing to floating, if they're floating, that means they're not flying up in the air, they're not falling down. That means the forces are balanced. So in this case, the gravity force is balanced by the electric force. The gravity force is mg, the electric force is Q times E. From what we just did, we know that the voltage is equal to E times D. So if we rearrange, E equals V over D, substituting that in, we get mg equals, so this is going to go up here, mg equals QV over D. To help me remember that, I'm going to flip the D to the other side, and I'm going to say mgd equals QV. That is a cool little equation that we can use when anything's floating between parallel plates. There's kind of four things in there, the M, the D, the Q, and the V. If I give you three of them, you should be able to rearrange and solve for the fourth. Take a bit of time, work through the example, think about it. I kind of spoiled it. The concept of floating is forces, and I'm going to keep rolling this video, but pause this video and go through those other ones to make sure you learn about floating charges. That's important. The lab that you're going to do next is all about floating charges. Cruising right along though, we're going to do two things with parallel plates. The first one was floating charges. The next one is accelerating charges. This is the technology that's used in old school CRT cathode ray tube TVs. If you've ever seen an old computer monitor or old TV, way in the back, oops, I've already highlighted it, way back here is a parallel plate. Here's kind of a bigger version of it. Depending what you want to shoot, let's say you want to shoot a little negative particle. If you make the back plate negative and the front plate positive, the little negative you drop in there is going to get attracted towards a positive plate. If you line up a little hole in that front plate, your little negative is going to end up here zooming away from the positive plate at some speed. It's a really cool technology. Here's in the little doodle of how I'm going to draw it. There's different ways to do it. Usually somehow like with a ground wire, when you plug something into the wall, they use the ground wire and they drop little negatives in between their two plates and then have a hole in the front plate so that the little negative ends up over here zooming away. the concept when shooting something, so think back to those check-ins we did on purpose. I gave you a check-in with a spring, and a spring was used to shoot a toy car or something. When we're using a device to do work for us, to push something around, to make it move, the concept related to that is energy. So if we're using a parallel plate to fire something, it's a conservation of energy thing. The electric energy stored in that the field delivers to the charge gets converted to the kinetic energy of the charge. Electric energy, from what we talked about before, is Q times volts. Kinetic energy is 1/2 mv squared. So we get a new equation. Our last equation for floating was Q volts equals mgd. Our equation, it doesn't really simplify beyond this. Our equation for shooting something is Q volts equals 1/2 mv squared. We can't cancel out the v. The capital V is volts, the little v is speed. That's kind of a quick talk through. Make sure you pause, go over those videos for examples 1 and 2, some examples 3 and 4. Make sure you go through these and make sense. That's where I'm going to pause this video. There's a worksheet with more to practice. This is a check-in exactly related to parallel plate stuff, and this check-in is setting up what we're doing in the lab to get you thinking about looking for patterns and numbers. Check-in 3-4 seems a little bit weird, but it'll pay off for the lab. That was a little bit quick. Watch the little videos, and if you have any questions about anything, just shoot me an email.